Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW English. So, students, today we are going to start with our next lecture based upon the chapter Coordination Compounds under our batch Excellence Batch. I hope so you have seen the previous lecture and all the topics were clear to you. So, in previous lecture, we got to understand about Werner's coordination theory and about valence bond theory. And today is going to be the most important session. So students, kindly pay attention to this lecture and do prepare your notes. So before starting this session, let me tell you one thing. Believe in yourself and that you are all there. Know that there is something inside you that is greater than any obstacle. So no matter how hard the life is, no matter how worst the situations are, trust in yourself that you are stronger than all of these obstacles. You can achieve anything in your life if you want to, students. So with this quote, we shall start our today's session with a beautiful smile. Today we are going to do lecture number 4th based upon the chapter Coordination Compounds. So as I was talking about this particular session, the coordination compound, today's lecture, what are the topics we are going to cover today? Students, in the previous lecture, we understood about valence bond theory. But in today's session, we are going to understand about crystal field theory, and we observe crystal field theory in 3 different complexes. So today we are going to see the crystal field theory with respect to the octahedral complex. If you got to understand the very first concept, that is the octahedral one, then you will automatically be able to understand about the tetrahedral one and the square planar one, because they are very simple. So it's just a matter of single topic that will lead to you to understand all of these topics. Great. So what are the topics we are going to cover today? Yes. Topics to be covered. They are, first of all, we shall understand about crystal field theory. Then students, we shall understand in depth with regard to the octahedral complex. So then we'll see crystal field theory in octahedral complex. Then we are going to understand the crystal field theory with regard to the tetrahedral complex. Great. Okay. So students, if you remember in the previous lecture, we understood that what shall be the coordination number when I am talking about octahedral complexes? Coordination number was 6. Okay. When I was talking about coordination number 4th, we observed 2 kinds of geometry. One was tetrahedral and another one was square planar. Also students, in the previous lecture, we understood with regard to the inner orbital complex and the outer orbital complex, if you remember. Yes. Okay. So before looking up to this topic, let us see that what is crystal field theory. First of all, let us understand what do you refer to as crystal field theory. Basically, in our valence bond theory, we understood that ligands were donating their lone pair of electrons to the central metal atom. This was the concept that we were studying from the Werner's coordination theory, and valence bond theory explained that in depth, that ligands are donating the electrons to the central metal atom, and central metal atom, are providing them the vacant orbitals so that they can overlap and create a coordinate bond. Yes, if you remember in the previous lecture, I told you that they will provide that much number of orbital that is equivalent to the coordination number of the complex. So basically, valence bond theory was focusing upon which concept? That coordinate bond is formed between the ligand and the central metal atom. Also, the metal atom, central metal atom, provides the vacant orbital to the ligand to interact. This was the concept, but crystal field theory is based upon a different concept. It explains that there is an electrostatic attraction. What is happening over here? Electrostatic attraction. So basically, it is an electrostatic model. Now you shall be thinking, ma'am, how it is electrostatic attraction? How you can say that? Crystal field theory is based upon the point charge particles. Basically, they consider each and every anion, or I would say the neutral molecules, as point charges and as point, cations and anions. So basically, if I talk about cations and anions, they are point charges. Are you getting my point? And if I talk about the neutral molecules, they are referred to as the point dipoles. Okay, so see over here, what does it states? Crystal field theory is an electrostatic model, which I told you that there is an electrostatic force of attraction. The positive and the negative charges attract each other. Okay, which considers the metal ligand bond to be ionic. Ionic refers to as cations and anions. It refers to that concept. Okay, arising purely from electrostatic interactions between the metal ion and the ligand. Now, till now, we were studying that the ligand are donating the lone pair of electrons to the central metal atom, and they are creating a bond between them, and the bond is the coordinate bond. Hence, the complex is the coordination complex. But today, the crystal field theory has explained to you people that it's not true. There is an ionic interaction, a positive and negative interaction is there that you shall be observing between the cations and the anions, or between the ligands and the central metal atom, that I would say. So, what does it state? That there is a purely electrostatic interaction between the metal ion and the ligand. Now, ligands are treated as point charges in the case of anions, okay, or point dipoles in the case of neutral molecules, which I have just spoken you right now. How are ligands considered? They are considered as point charges, while I am talking about whom? I am talking about anions. And they are considered as point dipoles in the case of whom? Point dipoles in the case of neutral molecules. Are you getting my point? Now comes the most interesting topic that they say. The 5d orbitals in an isolated gaseous metal atom have same energy. Now coming to this topic, the 5d orbitals. What are the 5d orbitals? You have studied in your class 11 chapter. In chemical bonding, you might have seen, while you in atomic structure. Not from the chemical bonding, yes, but there was some concept. Okay, coming to atomic structure chapter, you have seen the shape of the orbitals in the chapter atomic structure. Yes, if you don't remember, let me tell you. If I talk about d orbital, okay, so there are basically 5d orbitals. Which one? It is dxy, it is dyz, it is dxz, it is dx square, y square, and it is dz square. Am I right? Yes, ma'am. So what are the shapes of these orbitals? Let us draw the shapes of these orbitals in order to understand the concept in depth. Okay. If I talk about dxy, dyz, and dzx, here what happens? Here in these three cases, my dear students, you shall see that the lobes, basically if I talk about d orbital, it shows a double shape. So the lobes in the case of d orbitals lies in between the x's. What I'm saying? The lobes lies in between the x's. Okay. While if I talk about dx square, y square and dz square, over here the lobes lie on the axis. What happens over here? Here lobes lie on the axis. Is it clear? Now what is happening in both of these cases? We need to understand, we need to focus on them. Let us draw the structure for them. See, first of all, if I talk about dxy, first of all, let us talk about dxy over here. Okay, let us observe over here. First of all, I am making dxy. That means here I shall take x-axis and y-axis respectively. If this is my x-axis and this is my y-axis, I told you that the lobes lie in between the axis. That means the double shape, the double lobes over here would lie like this. This is the structure of whom? This is the structure of dxy. Okay, now if I'll draw over here dxy, we have already done dyz. So let us say take this as z-axis and this is y-axis. So again the lobes shall lie between the axis. Now it only depends. See, I am drawing it on a 2D plane. They are basically the 3D structures that you observe, the x-axis, the y-axis and the z-axis respectively. So you shall see these structures in 3D example, but here as I'm drawing on this 2D plane, so what I'm doing is I'm assuming that this is my z-axis and this is my y-axis. Am I right? Okay. Now this is our which one? This is referred to as dyz. Now coming back to this one here, as I have to draw dxz, so I'm assuming this as x-axis and this as z-axis. Again the lobe shall lie in between the axis. That means like this. Is it clear to you? Is it clear to you? Now coming to the concept of dx square y square and dz square, how shall I explain this? See. Over here, my dear students, what is happening? The lobes will lie on the axis. Now as here, let us say this is x-axis, y-axis. Lobes will lie on the x-axis, on y-axis, on x-axis. Then this is referred to as dx square y square. And if I talk about dz square, what I am talking about, dz square, that means this is our z-axis and you can take this as x and y respectively. In the case of dz square, you shall see that lobe will lie on z-axis and one lobe will be like this, in the form of a ring. Okay, so this is basically the dz square case. Am I right? Am I right? Now you all are aware of all of these 5D orbitals that we observe. Yes, so basically what is the line written over here? The 5D orbitals in an isolated gaseous metal atom or ion have same energy. That means they are degenerate. Now let me explain you this word degenerate over here. Now you have seen all of these shapes, right? Right. Very good. Okay, students, before explaining this to you concept, let me draw this structure first of all so that you can get it very easily. See here, as I've told you about all the shapes. Now what do we do over here? We will be drawing this structure particularly. See. Okay. First of all, see this line, then we'll draw an octahedral shape and I'll let you know x-axis, y-axis and z-axis all together. See, what do you refer to as degeneracy? See, when I'm talking about, you know that basically there are 5 orbitals like this. Okay, and how many electrons shall be present inside it? You can automatically tell them because each, will contain 2 electrons. That means 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So how many electrons are present? Maximum of 10 electrons can be exhibited in the d orbital. We know this thing. Now initially, students, what happened? These 5 d orbitals that I have drawn over here, dxy, dyz, dz square, dx square, y square, dz square respectively, they will have same energy. Now whensoever all of these have same energy, they are referred to as the degenerate orbitals, and this is basically the degeneracy. So what happens now? How will this degeneracy break in? What is the role of it in octahedral complex? Let me explain you. See, this degeneracy is maintained if a spherical symmetrical field of negative charges, now they are referred to as ligands, okay, surrounds the metal atom. However, when this negative charge is due to ligands, I told you, they are basically the ligands which are surrounding the central metal atom from all of the sides. Okay, so either the ligands can be anions or they can be the negative ends. Why we are always talking the ligands in case of anions or the negatively charged particles? Because ligands are the ones that contains lone pair of electrons. Basically, they are ligands. Ligands are the one which already have lone pair of electrons and which have a tendency to donate that lone pair of electrons to the central metal atom. So that's why if it carries a negative charge, that means it has electrons on it so that it can donate it further. Am I right? Great. Now students, see over here, some examples they have also given you over here, that yes, you can see these examples also in a complex. It becomes asymmetrical, degeneracy is lifted. Now to explain you what is written over here, let us see in the case of octahedral complex. So when I am talking about octahedral complex, just observe very carefully. See, now let us consider that basically we have central metal atom over here. Let us assume we have central metal atom over here, right? And I am telling you that students, this is your which axis? I am considering basically that now this is basically like this. As I'm drawing it on 2D, so it is basically like this. Now this axis I am referring to as your z axis. If it is positive z, then it will be negative z axis. It will be negative z axis. Okay. Now if I am saying that this is your x axis, then obviously this will be your minus x axis. Similarly, if I say this is your y axis, then this will be your negative of y axis. So basically this is the structure I am drawing it like way. Okay. Z axis, x axis, y axis respectively. As I'm drawing it over here, so I made in a 3D kind of a structure. Now just observe that what is going to happen. First of all, we shall draw the d orbitals over here. Which d orbital? See, you know that dx square y square and dz square lie on the axis. So if I'm going to draw the dx square y square, it will lie on the x axis and the lobes will lie on the, let me draw it a bit more clear. It will lie on the y-axis and on the x-axis respectively. Like this, they are lying on the axis. Now this I have made the x square y square. I have just shown you right now. You can even see in this particular diagram I have made it over here. See. This one. Lobes will be present on the x-axis and on the y-axis, both of them. So what we shall see over here, just look in the structure. It is lobes are present on the x-axis, on the y-axis. Other than this, lobes shall be present where, my dear students? You shall see that lobes will be present. See, this I am drawing dz square like this. Lobes are present on the z-axis as well as there is a kind of a ring-like structure over here. So what is happening over here? As I am talking about coordination number 6, that means octahedral complex. What will happen? 6 ligands. What do you refer to as a coordination number? Coordination number is basically the number of donor atoms present in a particular complex, in a particular compound. So if coordination number is 6, that means 6 donor atoms are approaching the central metal atom. So let us say that here are, like this we have just drawn 4, 5 and 6. Let us say that these are the 6 ligands that are approaching towards this central metal atom over here, which is present like this. This is central metal atom and all of these ligands are approaching. Now what will happen? Basically when we were observing this, we were saying that these are the 5d orbitals. These are the 5d orbitals which were initially present before the arrival of the ligands. They were 5d orbitals. Now what happened, my dear students? Ligands approach. When ligands came nearby, what will happen? As you all know that these orbitals, there is a central metal atom and the ligands when approaching, as we have just told you right now that there shall be the electrostatic attractions between over there and there will be a repulsion. Electrostatic repulsion will occur between the electrons and between the orbitals electrons. So what will happen over here? When repulsion will occur, its degeneracy, that means the same energy level shall break down. Now when it shall break down, first of all the energy shall change. The energy level shall change. Now what will happen? The ligands will come more closer. When they will come more closer, they will align themselves. Now what will happen? They will align themselves in such a way that one of the ligands shall be present over here, one over here, another over here, here and here. Now when they come so close, they align themselves in such a way that what will happen? Here ligand is approaching in this direction. Here ligand is approaching in this direction. Here ligand is approaching in this direction. Here ligand is approaching in this direction and in this direction respectively. Are you getting my point? So what is happening? Now when ligands are approaching from this direction, that means they are approaching towards which orbitals? Towards dx square y square and towards dz square. Are you getting my point over here? See, if I talk about dxy, dyz, dzx, they are the ones in which the lobes are present in between the axes. Over here, if you want to see in the dotted form, they will be here, no, in between. In between. Are ligands approaching from there end? No, ma'am. Ligands are approaching from which end? dx square, y square and dz square. Ligands are approaching from this end, from these ends. That means what is going to happen next? When the ligands are approaching from these orbitals, hence their energy level shall change and they will occupy higher energy level. Which one? dx square, y square and dz square. While the other three, dxy, dyz and dzx will acquire low energy. Is it clear? Okay. Now these are referred to as Eg orbitals. These are referred to as T2g orbitals. Are you getting my point? They are referred to as Eg orbitals. They are referred to as T2g orbitals. Great. Okay. Now I shall make this diagram over here a bit so that you can easily draw. I'll make it over here again. See. Initially there were 5 orbitals. Then the degeneracy broke down. And after that, what will happen? After that, you will be seeing that the ligands were approaching from the ends where the x square, y square and dz square was present. So they will be having a higher energy, and the dxy, yz and dzx shall have lower energy. As I've told you, they are referred to as Eg. Here G basically you can see, and this is T2G. Okay, this is due to the degeneracy. This is due to the degeneracy. Here they were having the same energy, so they were degenerated. After that, the degeneracy broke down because the ligands were approaching quite close to the central metal atom. Now, students, understanding this in more depth, you need to know more things over here. That here, if you draw this line furthermore, you shall see that this is referred to as a barycenter. Also, there are some few key points that you need to keep in your mind, such as the distance from this to this is positive 0.6 and the distance from this to this is minus 0.4. Is it clear? Is it clear? And all over, if I talk about this is delta naught. This is referred to as delta naught. O here refers to as for octahedral complexes. We are talking with regard to octahedral complex. So octahedral is written over here. Is it clear to you people? Now students, here we shall be seeing the various cases in which we are going to equate electrons. Now I have told you how this is made, how this is now referred to as crystal field splitting diagram. This is referred to as what? This is referred to as crystal field splitting diagram. Now students, we shall be calculating the value of the crystal field splitting energy. Okay, one more thing. Sometimes students ask that, ma'am, why this value is positive 0.6 and why this value is of negative 0.4. Now just understand over here, it is very simple concept that you will get to know. Here are 3 orbitals and the value 0.4. So we shall say 3 orbitals into minus 0.4. It is minus of 1.2 delta naught. And if I talk about these, there are 2 orbitals. So basically it is 2 into how much? Positive of 0.6. That means it is positive of 1.20 naught. So when you add this positive of 1.20 naught and the negative of 1.20 naught, you will get 0 value. That means this is the barycenter value. So they are equally divided in sort of energies. Now coming to the things that are mentioned in the NCERT, so that we can read it and we can move along with that topic as well. Crystal field splitting in octahedral coordination entities. Let us understand. In an octahedral coordination entity with 6 ligands. Now in octahedral, we already know that here the coordination number, ma'am, it's 6. That means 6 ligands shall be approaching from all the ends, right? 6 ligands surrounding the metal atom or the ion. There will be repulsion between the electrons in the metal d orbitals and the electrons for the negative charges. Now what will happen? The central metal atom do have electrons with it. So there shall be repulsion between the central metal atom electrons and between the electrons of the ligands. Am I right? So due to that repulsion, such a repulsion is more when the metal atom d orbital is directed towards the ligand. As I was saying, initially there was a central metal atom. Ligands were quite far away at a distance from each other. Now when they were coming close, the degeneracy broke down. There came repulsion between them, between the electrons of the central metal atom and between the electrons of whom? Of the ligands. Great. Due to which you can say See, they say such a repulsion is more when the metal d orbital is directed towards the ligand. Now, the ligands which are approaching in direction to the central metal atom will face more repulsion in comparison to the other atoms, right? Which I have shown you already with the help of diagram, that these orbitals in which the ligands are approaching, that orbitals will show more repulsion. This one, dx square, y square and dz square. That's why they have more energy in comparison to dx squared, dxy, dyz and dzx. Here you can even write it down. This is, let us take another color. This is dxy, dyz, dzx, and this is dx square, y square, and this is dz square. Am I right? Is it clear? Clear. Very good. Let us move forward, students. See, what does it says? The dx, this is all the thing which I have already told you. I have just written over here so that NCERT lines can also be completed, you know. You can read NCERT side by side. Let us see. Dx square, y square and dz square orbitals which point towards the axis along the direction of the ligand will experience more repulsion, which I have already told you, and will be raised in energy automatically. Here you can see they are being raised in energy automatically because they are facing more repulsion, because ligands are approaching from their ends only. That's why. Now see, the next thing they say that the dxy, dyz and dzx orbitals, if I talk about, which are directed between the axes, in between the axes, you know, they will be lowered in energy relative to the average energy in the spherical. Now see, this was the average energy and they are lowered by that energy. They are even lowered by that energy. They both experience repulsion, so they have higher energy than the expected one, then the very center one, and they have the less energy, so they have less energy than the very center one. So simple, quite simple. Great. Now let us see over here. Next thing. Thus, the degeneracy of the d orbital have been removed due to, now degeneracy was what? Degeneracy was equal energy in all the d orbitals. That was degeneracy. Now what happened, students? It broke down. How it broke down? It is mentioned over here. See, thus the degeneracy of the d orbitals has been removed due to the ligand electron metal electron repulsion, due to the repulsion in the octahedral complex, to yield 3 orbitals of lower energy. Now, which 3 orbitals had the lower energy? dxy, dyz, dzx. Great. See next. T2G set and the 2 orbitals of the higher energy EG set. EG set will have a higher energy. T2G set will have a lower energy, which I have already told you. This splitting of the degenerate levels due to the presence of the ligands in a definite geometry is termed as what? Crystal field splitting. And the energy separation is denoted by delta O. The subscript O is written for octahedral. This also I have told you. So see, you have read from NCERT. Now I guess this concept is also clear to you. Now see, thus the energy of the 2 EG orbital will increase by 3 by 5 delta naught. That means positive of 0.6 delta naught. And the 2T2G orbital will have 0.4 delta naught. They are lowered, so the value is minus 0.4 delta naught. Minus 0.4 delta naught. Is it clear to you, people? Great. Kindly, you can underline this in your NCERT. Also, you can draw these structures. Is it clear? Is it clear? Shall we move forward? Shall we move forward, my dear students, if it's clear to you, people? Now let's understand and draw the various structures. See, this is the diagram from the NCERT. This is the diagram from the NCERT. Let us read them. See what is happening over here. This is your central metal atom and this blue represents the ligands that are approaching. Now ligands can approach from any of the end towards the central metal atom. They were approaching. Yes, they were approaching. There came a time when they came so close that the repulsion increased. Degeneracy broke down and they assembled themselves in such a way. They assigned themselves in such a way that the ligands assigned themselves where the orbitals were seen as on the axis. For example, dx square, y square and dz square. So they approached in that directions automatically. Right? Now see, they have aligned themselves as in that way. Okay, in the octahedral complexes, these were the 5d orbitals. Their degeneracy broke down and the energy level increased when the ligands were approaching. As soon as they approached so close, the degeneracy shall break and the 2 EG1, that means dx square y square and dz square. They will have a higher energy level, and the T2G1, that means dxy, dyz and dzx, they will have the lower energy, which is referred to as T2G. They are referred to as the T2G1. Now the difference between both of them, the difference between them is delta naught, which is represented to you here. Delta naught, or O you can say, is representing the octahedral complex. Is it clear? Moreover, this is the barycenter. Okay, the energy level more than the barycenter is for the EG1 and the less than for the T2G1 in the case of octahedral. Do remember, do not apply this on all the cases. In tetrahedral and square planar, you shall see the different cases. But in octahedral, you shall see this way. You shall see this way. Is it clear? This is the average energy. Average energy. Now, EG1 have more energy than the average energy. EG orbitals, that means dx square y square and dz square, have more energy than the average one, while dxy, dyz, dzx have lower energy than the average energy. Is it clear to people? Great. Great. That is d orbital splitting in octahedral crystal field. Okay. Now this is the order of strength, students. This is the order of strength. This I shall come back to you when I will explain you the strong field and the weak field ligands. First of all, let me explain you one more thing. See over here, if I talk about crystal field splitting energy, if I talk about crystal field splitting energy, see, if I talk about crystal field splitting energy over here, what we are going to see, first I'll draw and then I'll write directly. See, we have 5d orbitals like this. Initially, they will have more energy as degeneracy breaks, and after that we have two orbitals, that is the EG1, that is dx square, y square, dz square. These are the EG1s. They will have more energy, and then we have the dxy, dyz and dzx respectively, which will have the T2G1 will have the lower energy with respect to the average energy. Am I right? Am I right? Over here, one more thing I told you, that this gap basically will have positive 0.6 delta naught value, and this will have minus of 0.4 delta naught. Also, students, write over here delta naught. Write over here delta naught. Great. One more thing. I wrote spelling wrong. Sorry for that. Okay. Crystal field splitting diagram. Now coming back to this. How to fill electrons in them, just understand. If I talk about, if I say you have been provided with there are two cases. Now before filling this also, you will be seeing that ligands basically are of two types, which I've already told you in the previous lecture. One is the strong field ligand, another one is the weak field ligand. This is the strong field ligand and this is the weak field ligand. Now when I talk about the strong field ligand and the weak field ligand, in the case of strong field ligand, you shall be seeing the pairing is occurring, while in the case of weak field ligand, there is no pairing. This I have told you in the previous lecture as well. Here pairing will occur. Here pairing will occur. While in the case of weak field, no pairing occurs. Am I right? Now students, look over here what is going to happen next. Now we need to fill the electrons. We need to see that where pairing will occur, where pairing will not occur. So I'm talking first of all about weak field ligands. Here you will write the configuration. Here you will write the representation. And here you will calculate CFSE value, that is crystal field splitting energy value. Okay, let us do now. See, initially let us start. Initially let us start with D1. For example, you have one electron in this. For example, you have one electron. You have one electron. You have one electron. Basically, initially their energies were equal. After that, it became higher level. And then when you are filling electrons, do remember, first you will fill electron over here, second over here, third over here. Okay, now if you are talking about weak field ligand, there will be no pairing. No pairing. So fourth electron will go over here. Then the fifth electron. Then sixth, seventh, eighth, ninth and 10th. Like this way. But if you are talking about strong field ligand, how you will fill electron? 1 electron, 2 electron, 3 electron. Now pairing will occur. Fourth electron will come over here. It will not go above. In strong field ligand, pairing will occur. What will happen? 1, 2, 3 and again 4, 5, 6. Then it will go above. 7, 8, 9, 10. But in the case of weak field, what will happen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like this way. Initially, everyone will be filled in the case of weak field ligand because there is no pairing at all. So, we are talking about first of all a weak field. If there is 1 electron, representation, let us draw over here. Representation, see this is T2G. T2G are 3 orbitals and this is EG. This is T2G, this is EG. In T2G only 1 electron, so I have represented like this. How to calculate the CFSE value over here? The CFSE value is minus 0.4. How many electron? 1. So it is minus 0.4 into 1 plus. Is there an electron over here? No. So 0 into positive 0.6. What will be the value? Minus 0.4 delta naught. Is it clear to you? Okay. Now for the next one. For the next one, if we have D2 electrons, if 1 electron, this is first electron, second electron. First electron, second electron. Now how many electron? 2 electron, ma'am. 2 electron. Let us represent over here. T2G, you will show 2 electron, 1, 2 and in EG, no electron. Because initially you have to fill first of all the T2G and then you will move forward to the EG one. How you will calculate how many electron? 2 electron. 2 into, what is the value? Minus 0.4 plus 0 into positive 0.6. What will be the value? It will be minus 0.8 delta naught. Now for the next case, let us see. Let us draw on the another page. Till then I want you all to write it down. Till then I want you all to write it down. Kindly write it down, students. Okay, now let us talk about D3 over here. And this is T2G, this is EG. T2G, EG. Here D4, T2G, EG. D5, T2G, EG. D6, T2G, EG. D7, T2G, EG. D8, T2G, EG. And D9, just see over here. In D3, initially it will be filled 1, 2, 3. T2G are the lower ones. Here I am not making this diagram again and again. T2G refers to this one, EG refers to these two. Okay. So in this case, 3 electrons, see T2G value has what? 3 into minus 0.4. So minus 1.2 delta naught, this value. This is 0 because there is no electron. There were 3 electrons that were automatically filled over here. Now coming to the D4, see. As I told you, it is weak field ligand. In the case of weak field ligand, no pairing. So what will happen? 1, 2, 3, 4. See over here, like this. If I fill over here, it is 1, 2, 3, then 4. It is weak field ligand, no pairing. The fourth electron will go to the T2G level. Fourth electron will go to which level? The T2G level. Is it clear to people? Okay. Now see over here. Now see over here, to calculate the value, they have minus 0.4 value. So it is 3 into minus 0.4 plus 1 into positive of 0.6. So what we will get? Minus 1.2 plus 0.6. Hence answer will be minus 0.6 delta naught. Answer will be minus 0.6 delta naught. Now see the next one. Now in the case of D5, what will happen? 1, 2, 3, 4, 5. There will be no pairing. See. 1, 2, 3, 4 and 5. No pairing, weak field ligand. So how you will calculate it? It will be 3 into minus 0.4 plus 2 into positive 0.6. It is minus 1.2 plus 1.2. So it is 0. It is 0. Now coming to D6. See. It is 1, 2, 3, 4, 5. Now 6th electron will come like this. It will pair up. See over here. It will be 1, 2, 3, 4, 5 and 6th will come like this. Clear? Okay. So how many electrons over here? 4 electrons. 4 into minus 0.4 plus 2 into positive 0.6. It is minus 1.6 plus positive 1.2. So it is negative of 0.4 delta naught. Is it clear to you people? Is it easy? I guess this is easy. Yes, you can easily do this. Let us see the next one. If I talk about D7, if I talk about whom? If I talk about D7 configuration. See, in the case of D7, it is again 1, 2, 3, 4, 5, 6 and 7. So you need to write the answer. This you have to calculate on your own. I'm just filling the electrons. Now I have done till D6, D7, D8, D9 and D10 answers. CFSE values you have to write by your own. How many? 1, 2, 3, 4, 5, 6, 7. Now see, 8. 1, 2, 3, 4, 5, 6, 7 and 8. Is it clear to people? Great. Now if I talk about D9, it is 1, 2, 3, 4, 5, 6, 7, 8 and 9. How I will fill the electrons in D10? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Is it clear to you all? It was simple. This was for weak field ligand. For whom? For weak field ligand. Now we shall do for whom? For strong field ligand. Let us do for now strong field ligand. See, if I talk about strong field ligand, students, now in the case of strong field ligand, what will happen? Pairing will occur. Let me show you some example. These are the d orbitals. They will have more energy because the degeneracy broke down because the ligands were approaching. Right? The EG ones will have more energy in comparison to the T2G one. Am I right? These are the EG ones. This is the T2G one. Right? So this is basically d or dx square y square and dz square, and it is basically dxy, dyz and dzx respectively. Am I right? Now students over here, see when I'm talking, let us take an example of D5. Okay. That means 5 electrons you have to fill. So 1, 2, 3, 4, 5. Okay. Again 1, 2, 3, 4, 5. What will happen now? What will happen? See. 1 electron, 2 electron, 3 electron. Now 4th electron will go over there or not? No, it will not go. Because in strong field ligand, pairing will occur. First of all, these will get filled up and then they will fill up. Sorry. In the case of weak field ligand, initially we used to fill 1 electrons in all of the orbitals because there was no pairing. So the electrons used to go above in the EG level, but over here this does not occur. What will happen over here? First of all, initially the electrons will fill in the lower energy levels and then they will move to the higher energy levels. They will get paired up altogether. Now if I'm talking about 5 electrons, it is 1, 2, 3, 4 and 5, like this. 5 electrons in such a way are assigned, right? So now if you need to calculate the value, again you can calculate the value. You already know this is minus 0.4 and this is a positive 0.6 delta naught, and the difference between this is delta naught. Is it clear? Now we can calculate similarly for the strong field ligands. Now let us calculate for the strong field ligands as well. For strong field ligand as well, if I am writing over here that the configuration shall come out over here, we will be writing configuration over here and then we will be writing the representation over here just as we did in the previous case, and then we are going to write one more thing, that is the CFSE value. That is which value? The CFSE one. Now if I talk about the configuration, here we have D1 configuration. Again the representations are done in such a way. This is your T2G, this is your EG level. Now if I'm talking about T2G, only 1 electron shall come over here. So what will be the CFSE value? You will calculate again over there. 1 electron into minus 0.4 plus 0 into 0.6. So the answer comes out to be minus 0.4. What it comes out to be? Minus 0.4 delta naught. Delta naught. By this way you will calculate it. Okay. Now see, in D1, D2, D3 you automatically can calculate, but in D4 where pairing occurs, I'll let you know that. Let us take an example of whom? Of D4. Of D4. In the case of D4, again these are the T2G, these are the EG. the T2G, the EG. Now 1 electron, 2 electron, 3 electron, 4th electron will come over here. No, ma'am. Why? Because pairing will occur. This will go over here in the T2G orbital only. So what you will get an answer over here? You will get how many electrons? 4 electrons into minus 0.4 plus 0 into positive 0.6. So you will get minus 1.6 delta naught. Are you getting my point? Are you getting my point? I want you all to write it down for once so that we can move on to our next part. Kindly write it down once. Yes, kindly write it down once. Okay, now let us do for D5, D6, D7 and all them respectively. Let us do for them also. See, again, if I talk about D5, here let us draw T2G, here let us draw EG. If this is your T2G, this is your EG, 1, 2, 3. Now, 4th will not go in the above higher energy level. It will go over here only, 4 and 5 respectively. Are you getting my point? So, what will be the CFSE value? 1, 2, 3, 4, 5 electrons in this. 5 into minus 0.4 plus 0 into 0.6 because there are no electrons in the EG energy level. So, what we will be getting here? Minus 2 delta naught. If we talk about D6 over here, T2G, EG, 1, 2, 3, 4, 5 and 6, my dear students. So again we can see 6 into minus 0.4, you'll get minus 2.4 delta naught. So by this way students, you can calculate all the energy level values one by one. Again, your homework question over here to calculate for D7, D8, D9 and D10 respectively. Just as you have to do in the previous cases. Calculate the CFSE values for all of them. Calculate the CFSE values for all of them. Is it clear to you people? Is it clear to you people? Great students. Now let us read this from the NCERT lines that we were observing. This is important. See, if I talk about weak field ligand and the strong field ligand, they have told you two major things over here. If delta naught, basically that is the difference between the energy levels, it is less than the P. What is P? P is the pairing energy. P is what? Pairing energy. If it is less than the pairing energy, the 4th electron enters one of the EG orbitals, giving the configuration T2G, 3 electrons and 1 electrons in the EG. Ligands for this are known as weak field ligands. What I've told you, in weak field ligands, there is no pairing. No pairing, so electron will go in the EG level. Electron will go in the EG level. If you are filling 4 electrons, 3 electrons will fill in T2G and 1 will be filled in EG1. This is the case for whom? For weak field ligand. That means in the weak field ligand, the delta E naught, the gap that you see in the weak field ligand is less than the pairing energy. While in the case of strong field ligand, the delta naught is more than the pairing energy. Is it clear? Now see, it becomes more energetically favored for the 4th electron to enter into T2G. That means pairing will occur. Electron will not go into the EG level. It will pair automatically in the lower energy level. That is what is happening over here with a configuration of T2G having 4 electrons and EG having 0 electrons over there. So what is happening? Ligands which produce this effect are referred to as what? Strong field ligands. And one more thing. Strong field ligands will form low spin complex, while weak field ligands will form high spin complex. High spin complex. Great. Now the electrochemical series tricks I'll let you know in the next lecture. So for today, your homework is to solve the practice sheet, students, that is being provided to you. Okay, and also read NCERT. So today we have covered the crystal field splitting in octahedral complex, and then in the next lecture we shall cover the tetrahedral ones, and the last one that we'll be seeing will be the square planar one. So after that we'll be seeing the bonding, one more topic that is left from your NCERT. So this shall end your coordination compound chapter in the next lecture. So I want you all to read this topic because questions are generally asked with respect to crystal field splitting in octahedral one, in tetrahedral one, and in square planar complexes. So this is the really very important concept because the crystal field splitting basically is based upon the electrostatic attraction. While if we talk about valence bond theory, it states that the orbitals were involved and there was an overlapping. So these are the quite different theories, and questions are generally asked in examination from this concept. So I shall meet you in the next lecture, students. I want you all to solve your practice sheets because the questions are being provided from the very good books and they are with regard to your examination as well. So till then, keep smiling, keep learning, students. All the very best.